Alright, this is our first video covering Chapter 5 for Math 1560, Calculus 1 at U of L for fall 2017. So this is going to cover section 5.1, and we're going to introduce the concept of an antiderivative here. So what is an antiderivative? Well, it's basically just reversing the process of taking a derivative, right? So somebody hands you a function f and says, hey, I want you to find some other function whose derivative gives you the one you started with, right? So basically what you want to think of here is you want to think of little f as, you know, a function that you obtained by doing some derivative, and now you want to reverse the process, right? So some simple examples we can think of are things like this. Well, since the derivative of x to the n is n times x to the n minus 1, then that tells me that an antiderivative, that's terrible handwriting, let me see if I can improve. An antiderivative of f of x equal to n times x to the n minus 1 is f of x equals x to the n, right? Similarly, f of x equals sine x is an antiderivative of little f equals cos. Okay. Let's do a couple more detailed examples. Well, let's be a little bit more careful about this this power rule one, right? So suppose I have f of x equals x to the n, and I want to find the antiderivative. Well, how would we have ended up with that x to the n, right? We got it, so we kind of think of this as we obtained this by taking a derivative. So we started with some other function, we took its derivative, we ended up with x to the n. Well, we've got a power, and so, you know, we probably can guess that this power came from some other power, right? So what happens when we take a derivative? When we take a derivative, we subtract 1 from the power. So for the antiderivative, we should add 1 to our power, add 1 to the exponent. Okay, so let's do that as a first step, x to the n plus 1, right? But now we think about, well, what happens when you take the derivative of x to the n plus 1, right? You get x to the n, but you also have to multiply by the power. You have to multiply by n plus 1. So how do we make sure that we don't end up with that number out front? Well, we make sure that something is there to cancel it. So we also have to divide by the new exponent. Okay, so we get this antiderivative. With one catch. There's one case where this isn't going to work, right? When does it not work? Well, I got to make sure I don't divide by 0, so that means n plus 1 can't be 0, so I got to make sure that n here is not equal to minus 1. What if n is equal to minus 1? Well, if n equals minus 1, that's x to the minus 1, that's 1 over x. Can we think of a function whose derivative is 1 over x? Yes, it's one that we've seen all the time. We have it on our list of standard derivatives. Here, we want to take, well, what's the function whose derivative is 1 over x? It's the natural log. But we should be a little bit careful. There are always domain issues that you want to think about. When you take antiderivatives, you sort of expect that the domain should at least include what you started with, right? When you take the derivative, the domain never gets bigger. At best stays the same, and the original function is defined everywhere except for 0. My antiderivative right now is only defined for positive x, but we know how to fix this. We've seen this before. We put absolute values in there, and we've worked that out in the past, that when you take the derivative of the log of absolute value x, you still get 1 over x. So we can take that as our antiderivative. All right. Now there's one other issue that we need to deal with here. Is this antiderivative unique? Is there only one antiderivative, or could you have more than one? Well, let's think about it. Suppose I have two antiderivatives for some function f. What does that mean? Well, that means that, so f prime of x equals f of x, and g prime of x equals f of x, right? They're both antiderivatives, so their derivatives both equal f. Well, that means that f prime of x equals g prime of x. What can we say about two functions that have the same derivative? Well, this would be the same thing, and in fact, these are two-way arrows, these go back and forth. This would be the same thing as saying that f prime minus g prime is 0, right? So in other words, the derivative of the function f minus g is 0. Well, what do we know about functions whose derivative is 0, identically 0, right, for all values of x? Well, we saw this back in chapter 3. This was a early test of the mean value theorem, that if we have a function whose derivative is identically 0, it has to be a constant, right? So that means that f of x minus g of x equals c, where c is some constant, right? And we might write it like this. We might say f of x equals g of x plus c, right? So the antiderivative isn't unique, right? You can always add a constant, and if we think about this, of course that makes sense, because if we add a constant to a function and then we take the derivative of the constant goes away. So there is no effect on the derivative if we add a constant. So that means that in fact there are infinitely many antiderivatives for a given function, because there are infinitely many constants that we could add. However, that's the only flexibility that we have, right? This tells us that if we have two derivatives, at worst they differ by a constant, right? We get from one derivative to another by adding a constant, so it's not so bad. Worst case scenario, we're off by a constant. That's something that we can handle. Alright, here's a list of some common antiderivatives. We've seen the first two, right? If f of x equals x to the n and n is not equal to minus 1, our antiderivative is 1 over n plus 1 times x to the n plus 1. And if you want, we could put that plus c in there, right? If we want to kind of give the most general answer. For x to the minus 1, we saw that's given by log of absolute value of x. Well, the exponential function is its own derivative, so that means it's also its own antiderivative. For sine and cos, you have to be a little bit careful. We're going backwards, right? So the derivative of sine is cos, which means actually we can do this one down here first. We're looking for a function whose derivative gives us cosine. We know that that's the sine function. So if we're looking for a function whose derivative gives us sine, well, we actually need minus cos, right? Because when we take the derivative of minus cos, we get minus sine, which gives me plus sine. And if you remember your inverse trig derivatives, there's a couple more that you can do here. This 1 over the square root of 1 minus x squared, well, that is the derivative of arc sine. 1 over 1 plus x squared, that's the derivative of arc tan. And of course there are many other ones that we could write down, right? And basically take any derivative that you worked out in chapter 2, you can reverse it, and now you have an antiderivative, right? So there's really an endless supply of these. Now, one last thing before we end this video. There is an alternate notation that you sometimes see, the indefinite integral notation. So we will be seeing this notation a little bit later on. It's kind of an odd notation now because we haven't really discussed integrals yet, but once we get to the fundamental theorem of calculus, we're going to see that antiderivatives play a fundamental role in integration, and so it makes sense that we have some kind of connection between the two and some kind of notational connection between the two. And the other thing is this makes it a little bit easier to write out some of these antiderivative rules, because now, for example, if I want to tell you what the antiderivative of x to the n is, I can say this: the integral, I just read, is the integral of x to the n dx is given by 1 over n plus 1, x to the n plus 1, plus our constant, and that's going to work as long as n is not equal to 1, and so on. I could do the same thing for any of those antiderivatives that we had on the previous page. Alright, so that's it for this video. In the next one, we're going to look at what exactly can we do with this constant that keeps showing up when we take antiderivatives.